Should we start? Okay, good morning. One of the last results we saw yesterday was the following theorem or proposition. If the utility function is quasi-concave, non-decreasing, and continuous, so if U has these properties, then the indirect utility function is convex if and only if this function is convex for every x. So that's to say, convexity of the indirect utility function is equivalent to a certain convexity along rays of the direct utility function. I mean, it's not convexity along rays because t comes in the denominator. Convexity along rays would be with t multiplying x, okay? But it's a property along rays. But in the differentiable case, what happens? So suppose U is C2. By C2 we mean that it's defined on a neighborhood of the orthant, on open neighborhood of the orthant, and it's C2 everywhere on that neighborhood. So it can be extended beyond the non-negative orthant. So if U is C2, then, well, and X is in R plus N, this convexity along rays property is satisfied if and only if what are the properties on the derivatives of U that correspond to this convexity property, then simply that X transpose Hessian of u of x plus 2 x transpose gradient of u of x is greater than or equal to 0. That's the property. Okay? And the proof is simple. Simply, let's give a name to this function. Let's call it phi. So I define phi from r plus plus into r by phi of t equal to u of x over t. And I will simply compute the second derivative of phi. And we will easily see that the second derivative of phi is non-negative everywhere if and only if this condition is satisfied. So it's just a matter of computation. Okay? So, phi prime of t is minus 1 over t squared, it's the derivative of t, x transpose gradient of u xt. Okay? Is this correct? The second derivative. It's 2 divided by t to the cube x transpose gradient of u at x divided by t minus 1 over t squared. Again, when I take the derivative of this part, I get again minus 1 over t squared, so in total I obtain 1 divided by t to the power 4. X transpose Hessian of u of x over t times x. And this can be written one t squared factor of. So I have taken 1 over t squared as a common factor. T squared is still left here. So this t squared, I put 1t here and 1t there. Okay? Is x over t transpose Hessian of u at x over t times x over t plus so after taking 1 over t squared as a common factor, here 2 over t is left. So here is the 2, and the t I associate to this x. Do you agree? So, if this function is convex, phi is this function, phi is convex. So its second derivative is greater than or equal to 0. If in this equality you take t equal to 1, second derivative is non-negative everywhere. So in particular, if you take t equal to 1, you get this condition. In the opposite direction, if this condition holds, this is the correct statement. If this condition holds, then in particular it holds for x into t. Okay? So for x into t, when you replace here x with x into t, then this expression becomes non-negative, and this is true for every t. So the second derivative of phi is non-negative everywhere, which means that phi is convex. Okay? Is this clear? It's just computing second derivatives. Then some immediate corollaries. What is the good eraser? Is this one? Thank you. So what are the conclusions, immediate conclusions? I mean, combining this theorem with this proposition, we get the following immediate corollary. If U is quasi-concave, non-decreasing, and C2, then the indirect utility function is convex if and only if this expression is non-negative. For every x. And another consequence, which is more interesting, is that if U is concave, U satisfies all these properties. And on top of these properties, it has no maximum. and it satisfies this inequality. Then the corresponding demand mapping is monotone. So this is a consequence of the result I presented and I proved, I think yesterday morning at the beginning, saying that if U is concave and has no maximum, and V is convex, then the demand is monotone. Sorry, here U is concave. So I'm using that result. U is concave and has no maximum. Well, here I need two extra conditions, non-decreasing, which is natural, C2, which is a technical assumption, because we need to work with derivatives. Derivatives is our main tool. It's a pity because it doesn't make part of the essence of the problem, but it's a powerful tool, as we all know. Okay? Then, if this condition is satisfied, then the demand is monotone because this condition is equivalent to convexity, to this convexity along race property, which is in turn equivalent to convexity of B. But, well, what about these assumptions? I said that U is concave economically has no meaning, but we can accept this condition. With a better statement would be if our preferences admit one representation which is concave, and for that concave representation we have this property, then there is monotonicity of the demand. But look, concavity for a C2 function means the Hessian is negative semi-definite. Then, if U is concave, this expression is less than or equal to 0. Okay? But we are adding here a non-negative term because x is non-negative and the gradient is non-negative too because U is non-decreasing. So we are adding a non-negative term which makes this inequality to be possible. But what this shows, it does concavity of U and convexity of V are somehow against each other. Okay, because this comes from convexity of V. Okay, and concavity of U is negative semi-definiteness of the Hessian. Here we are just using not every direction D. Negative semi-definiteness would be D transpose Hessian times X less than or equal to 0 for every D. And here we are using only X. But anyway, I mean, let's say if U is very concave, then this is very negative, and we will not succeed to get it non-negative even if we add a non-negative number. So the idea I'm trying to convey is that concavity of U and convexity of V are somehow conflicting. They are in opposite directions. They are not incompatible, but let's say the more concave U is, the less convex V is, in a sense. Okay? So the assumption, the result can be said is saying if U is concave, but not too much, okay, then the demand is monotone. Anyway, it may be nice to spend a couple of minutes by examining this result in a simple case, which is Leontief. I think I didn't do it yesterday. No? So let's look once again to Leontief. You remember that the utility function was the mean over I of xi divided by ai, where the ai are strictly positive constants. And then we obtain that v of p is equal to 1 over pa for p different from 0. Okay? For p equals 0, it is plus infinity. This function, I mean the function defined like this, 1 over pa. If p is different from 0, plus infinity, if p equals 0, this function v is convex. And so according to this theorem, this convexity along race property should hold. Does it? What is u of x over t? This is the minimum over I of xi divided by AIT. And this is 1 over t times the minimum of xi over ai. So it's linear, not only convex but even linear. So it works, at least in this case. Now, I mean, it's the first time we encounter a convexity along race property, but we will find it again. So a relevant question is which generalized convexity properties does a convex along ray functions enjoy? What do we mean by generalized convexity? From the following point of view. A function, an extended real valued function, is convex and lower semi-continuous and proper if and only if it is the supremum of a collection of affine functions. So the affine functions generate all lower semi-continuous proper convex functions by the operation of taking pointwise supremum. So is there something similar for convexity along rays? But first of all, I will discuss classical convexity along rays. So when T is multiplying, no dividing. So can you tell me a family of generators of all functions on the non-negative orthon that are convex along rays? Again, I'm testing your intuition. My intuition, I don't have any at this moment, but I had because the result I'm going to present is mine. And this is in the volume, this is in the paper I mentioned I wrote, published at the beginning of 2010, in that volume in honor to my friend and co-author Antonio Martinon from the University of La Laguna in Tenerife, Canary Islands, Spain, but in Africa. And when he turned 60. So the title is Convexity of Indirect Utility Functions. It's not available online as far as I know, but I have an electronic copy of the whole volume. And yesterday I was looking at it, and I was very interested to see that I proved the result inspired by Milleron, that if U is concave and no maximum and V is convex, then the demand is monotone. But I think I put some extra assumptions, but also my proof was very complicated, was using Lagrange multipliers. And this was also completely different from the one by Milleron. This means at that time, I didn't know the paper of Milleron. Okay? And in fact, I have forgot the specific details, but I remember that I sent that paper, maybe, or a previous paper, to a very good mathematical economist in Bonn, Germany, Reinhard John, belonging to the team of Werner Hildenbrand, a very famous mathematical economist, with this result or a similar one, and he said, have you noticed that you have proved more than what you have said? And essentially his idea was Milleron, and then later on I discovered Milleron. So, I mean, simple results do not necessarily come to your mind from the very beginning. So that result I'm going to mention now is published there, but it was also inspired by some previous related results about convexity along rays obtained by Alex Rubinov, very famous mathematician who unfortunately passed away in 2006. He was also my co-author and very good friend. He was Russian, but he was working in the last times in Ballarat, Australia, where he created an excellent group of optimizers. He was the first to arrive in Ballarat, but then he was coming, well, he was in Russia, formerly Soviet Union, and but he had been working in Baku. Then he moved to Israel. He was Jewish, but he didn't adapt. In particular, he had difficulties with Hebrew, with the language. He also, even when he was living in Australia, he claimed that he had difficulties with English. But I think it was his technique to avoid having to teach. No, I cannot teach, I don't know English. Okay? And then he was devoting all his time to research. Fantastic person, I can tell you. And then he was hired by Barney Glover, who later on moved to Perth, in Ballarat, and then he imported from the former Soviet Union a team of excellent researchers in optimization, in particular from Baku, where he was working in the last times. The leader of his group, after he passed away, since then until now, is another good friend of mine, and hopefully our co-author soon, Adil Bagirov. You may know this name. He has done very important job in numerical optimization. Okay? Good. So these are historical remarks and anecdotes. Our common friend Joydeep Datta, who may be watching this presentation or maybe later, was lucky enough to spend 1 year and a half in Barcelona as my postdoc long ago in 2000, more or less. And why I said he was so lucky, because the first 6 months he was sharing the office with Alex Rubinov, because Alex Rubinov came to visit me a week earlier or a week later than Joydeep did. Well, so let's go to our result. A generalized convexity property of convex along race functions. So it's the following theorem. A function on the positive orthant. Okay, I want to avoid problems with 0 components, but it can be dealt with. Okay? So this function is non-increasing. And convex along rays. In the classical sense, this means u of the function so I insist T is multiplying, unlike there. It's convex along rays, this is convex for every x in R++ n, if and only if there exists a subset of R++ n union 0 Cartesian product the reals such that f of x f is the maximum over LC in U of C minus the max, I from 1 to n, of Li times xi. So roughly speaking, a function is non-increasing and convex along rays if and only if it is the pointwise maximum of a collection of functions of this particular type. So functions of this particular type generate all non-increasing and convex along rays functions. These play the role as affine functions play in classical convexity. Affine functions generate all our semi-continuous proper convex functions. These functions generate all non-increasing convex along ray functions. These are in the same way as one can say affine functions are the elementary convex functions, then these functions are the elementary convex along rays functions. They are convex along rays because if I multiply this with t positive, then t comes out, so I get a linear function, an affine function of t. Okay? But affine function is not only convex, it's also concave. So these functions are both convex along rays and convex and concave along rays, both. Like affine functions in the classical convexity case, they are both convex and concave. So we find again result of this type, which we already saw in the quasi-convex setting. Quasi-convex, lower semi-continuous quasi-convex functions are pointwise suprema of lower semi-continuous quasi-affine functions. And quasi-affine functions are functions that are both quasi-convex and quasi-concave. So let's prove this statement. Is not difficult. The difficulty is something I will not help you to solve. Is where did you get the inspiration? I will start the second part of the proof by something which you will say, why? And I say, I don't know, I don't remember, but it works. Okay? And so, this is obvious. Okay? Because, as I said, each one is non-increasing, because when xi increases, then increases, but there is a minus sign, etc. So it's non-increasing, and convex along rays I already justified. Okay? So there is nothing to prove in this direction. So the opposite direction is the interesting one. And then, for the interesting implication, I have to prove that there exists u. I will tell you one u. That works. And sorry? wait a second. First of all, here there is something missing. But I think you are asking about here. Yes. The T is strictly positive. Ah, thank you. Thank you. Well, so to prove you the existence of U, I will tell you who is U. And then probably your reaction should be like my reaction yesterday when I saw my proof in that paper. Why this U? Okay, but then okay, I accept this U, you have to accept it too, and then we will see that it works. So I am preparing you to see a rather strange U. Okay? So U, I define U as the set of psi y minus 1. Y is a vector. So from now on, I'm going to, if y is y1, yn, and is non-zero, I mean, all components are non-zero, strictly positive, by y minus 1, I mean y1 minus 1, yn minus 1. Okay? I employ this notation. Fy plus psi belonging to R plus n union 0 cross R such that y is arbitrary in R plus n and psi belongs to minus the subdifferential of Fy at 1. A very natural U, as you see. Okay? Okay. I didn't say who is Fy. Fy from R plus into R is defined by Fy of alpha equals F of alpha y. So it's the function along y. Do you like this U? You may like it or not, but it works. So first of all, I'm going to prove that for every LC in this beautiful U, this function is a minorand of f. And later on, we will see that the maximum is attained and coincides with f of x. Then, so let's fix LC in U. So we know that L, okay. Then the function, the elementary function appearing there is. So what is C? Is f of y plus c. For some given y in R plus n, and some psi in the super differential of minus fy at 1. Okay? Minus the max of so what is Li? Li is C times yy to the minus 1. Okay? So when plug it into here, we get psi xi by yi. F of y is fy at 1. And here I can take minus c as a common factor times what? Because this comes out of the max. Because f is not increasing, so fi is non-increasing. Therefore, its subgradients are non-positive, its subdifferentials. Then psi is non-negative. Okay? So this makes possible that this belongs to R plus n, because it's but it may be 0. So if psi is different from 0, c y minus 1 is in R plus n. If c is equal to 0, this is in 0. Okay? By the way, in this direction, everything works if the first component in this product is R plus n. But one can take u in this set. Okay, times the max of xi over yi minus 1. And now, what's the conclusion? What do you know about minus xi? It's a subgradient of fi at 1. So use the subgradient inequality to conclude that this is less than or equal to fy the maximum over I of xi divided by yi. And now apply the definition of fy. It was non-increasing. Yes. Then how does this vector compare with x? Is any one of them larger than the other? Let's compare components. Component j with component j here. This, because this is the maximum and everything is non-negative, this is greater than or equal to xj over yj times yj, which is xj. Okay? So the comparison is this. So this vector, this is component-wise, so this vector is greater than x or equal to. And our f is non-increasing. Then when I decrease this vector by replacing it with x, then I am increasing the function value. So what have I proved so far? That the supremum, I still don't know if it is a maximum, that the supremum in this right-hand side is less than or equal to the left-hand side, f of x. But I want to prove equality. And I want to prove that the maximum is attained. So, given x, I should prove the existence of LC depending on this particular x, for which this is equal to f of x. This is what is missing. Okay? And then do you have a candidate for LC? You told me that U is a very natural definition. So now you should tell me which is the element in U that makes this job. So for which element we have equality? Then what if we take y equal to x, which is in R plus plus n and xi any subgradient with minus sign? Then if I take y equal to x, so this is xi, so this difference is 0, or if you want, come here, then because xi is xi, you have 1. That's okay, nothing new, but here yi is xi, so this maximum is equal to 1, and then I get, this is less than or equal to f of y, which I don't, yeah, to f of y, but y and x are exactly the same, because I have chosen y this way. Okay? Do you agree? So I have found a particular LC, just LS xi x minus 1. And C is f of x plus c. And this c is simply a minus a subgradient of fx at 1. So when you make this choice, you choose C in this set, and then this is L, and then you have this C, then you have equality. So the result is proved. It's very simple, and all this convexity along rays, and also on this area which we called, this is my paper, but we have other papers, and we are Jaydeep Datta, Alex Rubinov, and me. Some papers with the title Monotonic Analysis over Cones. In this field, there is generalized convexity of this type. Supremum of elementary functions are our functions. But there is something different with the classical theory, which makes that theory less powerful than the classical one. Namely, suppose you have a convex function, Lauer semi-continuous and proper, and I tell you a point in the domain. So you know that it's finite values everywhere. I mean, you know there is a subgradient. That is, you know that there is an affine minorant that coincides with the function at that point. But knowing just the value f of x, you cannot compute. So if I tell you, I have a convex function, and look, this is a point in the graph. You cannot tell me what is a subgradient. It can be anything. You know there exists one, but you need information, local information around. Here not. I'm just taking Li, which depends only on x, not on the behavior of the function around. So somehow this theory is less powerful because of that. Because it's, let's say, it's more evident from a geometrical point of view. That, okay, I think it's time to stop now. Thank you.
You're motivated to choose the set U consists of the subdifferential, including something related to subdifferential.
What was my motivation?
I think so.
I told you, don't ask me this question, because you are asking me about what I did 15 years ago. Okay, then I can't remember. It looks a little bit mysterious. But how do you get such things? You are working into the problem and then you play, and I mean, a previous question is, know how were you so smart to realize that this U works? A previous question is, what was your intuition to understand that these are the elementary minorants of a non-increasing and convex along rays function? Then I don't know, but when you are deeply working into something, you have ideas, and then you forget. Okay? No, I was probably inspired by similar results by Rubinov about convex along rays function. I think this is what I wrote in the paper I mentioned. I think this result is similar to the one in one paper, I think, by Glover and Rubinov. And, but I say the proof is very different. So you can find a result related to that one in the paper by Glover Rubinov that you will not find such a U, which makes their proof more complicated. More complicated, but maybe easier to understand. I don't remember the proof. I mean, not easier to understand. Here, I say, I introduce this U, and you say, okay, you are free to introduce whatever you like, but why? And then my answer is, wait and see. And so you see that it works, fine. Okay, but how did I know beforehand that it would work? I don't know. I don't remember. Okay? But this choice of U, the result may have been inspired by one of Glover Rubinov, but the definition of U, not. Is, let's say, my definition. I don't know where my inspiration came from, but not from Glover Rubinov. Okay. Okay, now really time to stop. Yes, maybe.